A hurricane large enough to swallow our entire planet whole, 1.3 Earths across, spinning at 400 miles per hour, raging for at least 400 years, possibly longer. This storm isn't made of water and air, it's hydrogen, helium, and ammonia, swirling in bands of toxic gas under crushing pressure. And it's not on some distant exoplanet barely visible through telescopes. It's here, in our own backyard, on Jupiter. This is the Great Red Spot. Everything you think you know about storms, forget it. Earth's most powerful hurricanes are nursery rhymes compared to this cosmic monster. Category 5, a gentle breeze on Jupiter. The storm you're about to meet laughs at physics, defies expectations, and holds secrets that could reshape our understanding of planetary atmospheres, climate change, and even the search for life beyond Earth. But here's what should really keep you awake at night. We don't know why it's red. We don't know why it's shrinking. We don't know how it survived centuries when it should have dissipated decades ago. And most terrifying of all, we don't know what happens when it finally dies. Strap in. We're going to Jupiter. Before diving into the Great Red Spot itself, you need to understand the hellscape that birthed it. Because Jupiter isn't just a bigger Earth with more storms, it's an entirely different category of world. A gas giant so alien that weather barely describes what happens there. Jupiter is 11 times wider than Earth. If our planet were a grape, Jupiter would be a basketball. It spins so fast, completing a full rotation in just under 10 hours, that the planet visibly bulges at the equator, squashed like a spinning top. This rapid rotation is the engine that drives everything terrifying about Jupiter's atmosphere. The planet has no solid surface. None. What we see are clouds, layer upon layer of them, stretching down perhaps thousands of miles into an ocean of liquid metallic hydrogen. The pressure increases as you descend, but there's no ground to stand on, no ocean floor to reach. Just gas compressing into liquid, then liquid compressing into exotic states of matter we barely understand. The atmosphere itself is a chemical nightmare. Hydrogen and helium make up most of it, but trace amounts of ammonia, methane, and water create the bands of color we see from space. These chemicals react under intense ultraviolet radiation from the sun, creating complex organic compounds that give Jupiter its distinctive hues: browns, oranges, yellows, and that unmistakable blood red. Temperatures range from about -145 degrees Celsius at the cloud tops to potentially thousands of degrees in the deep interior. Winds don't just blow in one direction. They form jet streams that circle the entire planet at different latitudes, moving in opposite directions, creating shear zones where storms are born, fed, and sometimes destroyed. This is where the Great Red Spot lives. In the southern hemisphere, nestled between two powerful jet streams moving in opposite directions, a storm caught in a cosmic vice that has somehow sustained it for centuries. First observation: 1665, possibly earlier. Astronomer Giovanni Cassini, yes, the Saturn probe is named after him, documented a permanent spot on Jupiter that year. Some records suggest observations as early as 1630. That means this storm has been raging since before the United States existed, before the Industrial Revolution, before Newton published his Principia. Think about that. While human civilization has risen, fallen, and transformed, while empires have collapsed and technologies have revolutionized our species, this storm has just kept spinning, unfazed, unstoppable. But what is it exactly? The Great Red Spot is an anticyclone, a high-pressure system rotating counterclockwise. On Earth, high-pressure systems bring clear skies and calm weather. On Jupiter, under these conditions, high pressure creates the most violent sustained vortex we've ever observed. The storm's dimensions are staggering. Currently, it's approximately 16,000 kilometers across at its widest point. That's roughly 1.3 times Earth's diameter. At its peak in the late 1800s, it may have been over 40,000 kilometers across, 3 Earths wide. Looking up from a nearby moon, you'd see a storm so large it blocks out a third of the sky. The storm rotates once every 6 Earth days. Its winds peak at around 680 kilometers per hour, 400 plus miles per hour. To compare, Earth's strongest recorded hurricane wind was 253 miles per hour during Hurricane Patricia in 2015. The Great Red Spot's gentlest breezes would shred that record. The storm extends vertically too, possibly hundreds of kilometers into Jupiter's atmosphere. Recent observations from the Juno spacecraft suggest the Great Red Spot is a towering structure, its roots reaching deep into the planet's interior, possibly connecting to the mysterious water layer that scientists believe exists far below the visible clouds. But here's the mystery that haunts planetary scientists. We don't actually know how deep it goes. The storm could be a shallow feature, a skin-deep blemish on Jupiter's vast face, or it could be a titanic column of rotating gas extending thousands of miles down, anchored to something deep in Jupiter's interior. We simply don't know. Every time we think we understand this storm, it reveals new layers of complexity. The red in Great Red Spot isn't just a name, it's a genuine mystery that has baffled scientists for centuries. Jupiter's atmosphere is primarily hydrogen and helium, colorless gases. The ammonia clouds that dominate the upper atmosphere are white. The various brown and orange bands are created by chemical reactions involving phosphorus, sulfur, and hydrocarbons. But red, intense, blood red, that's different. For decades, the leading theory involved complex organic molecules called tholins. These are created when ultraviolet radiation breaks apart methane and other simple molecules, allowing the fragments to recombine into larger reddish-brown compounds. Tholins are found throughout the outer solar system, giving color to everything from Saturn's moon Titan to distant Kuiper Belt objects. But tholins alone don't explain the Great Red Spot's intensity. Recent research suggests something more exotic. The storm's extreme conditions, its violent winds, its high altitude, its unique pressure and temperature profile, may be creating chemical compounds we haven't fully identified. The storm could be dredging up material from deep in Jupiter's atmosphere, exposing gases and particles that never see the light at normal cloud levels. Some scientists propose that the color comes from ammonia reacting with acetylene, creating a complex red compound. Others suggest sulfur compounds, or even exotic forms of phosphorus. The Juno spacecraft's instruments have detected signatures consistent with various possibilities, but nothing definitive. Here's the truly unsettling part. The Great Red Spot changes color, not subtly, dramatically. Historical records describe it as pale, pink, orange, and intensely red at different times. In the early 2010s, it appeared to fade significantly, worrying astronomers that the storm might be dying. Then, in 2014, it deepened to a richer red than observed in decades. What causes these chromatic shifts? Solar activity, changes in the storm's altitude, chemical reactions we don't understand. The storm seems to pulse with an inscrutable rhythm, its color a vital sign we can't interpret. If we can't explain why a storm is red, how can we claim to understand it? How can we predict its behavior? The color isn't cosmetic, it's diagnostic. And right now, Jupiter's most famous feature is sending signals we can't read. Since the late 1800s, astronomers have tracked the Great Red Spot's size with increasing precision. The data tells a disturbing story. The storm is getting smaller, much smaller. In 1879, when reliable measurements began, the Great Red Spot was approximately 40,000 kilometers across. By 1979, when Voyager 1 flew past, it had shrunk to about 23,000 kilometers. When Hubble started regular observations in the 1990s, it was down to 21,000 kilometers. Today, approximately 16,000 kilometers. The storm has lost roughly 60% of its maximum recorded size in just over a century. At this rate of shrinkage, about 900 kilometers per year in recent decades, it could disappear completely within 20 years. Some models suggest sooner, Some suggest the rate of shrinkage is accelerating, but here's where it gets weird. While the storm is getting smaller in width, it appears to be getting taller. Recent Juno data suggests the Great Red Spot is concentrating its energy, becoming more intense even as its footprint shrinks. Its winds haven't slowed. If anything, some measurements suggest they're speeding up in the storm's core. Think of a figure skater pulling in their arms during a spin. Conservation of angular momentum causes them to rotate faster. Is the Great Red Spot doing something similar, contracting its mass to sustain its rotation? If so, how long can that process continue? Even stranger, the storm is breaking up. High-resolution images show flakes or streamers peeling away from the Great Red Spot's edges, spinning off into the surrounding atmosphere. The storm is shedding material, bleeding into the bands of gas that flow around it. Some of these flakes are themselves massive storms, Earth-sized vortices that would be headline news if they existed anywhere else. But on Jupiter, they're just debris from the main event. Is this shedding a sign of terminal decline, or is it somehow part of the storm's life cycle, a way of shedding energy to maintain stability? Again, we don't know. We've never watched a storm like this die. We've never observed one being born either. The Great Red Spot exists in a timescale beyond human patience, its life cycle measured in centuries, its death potentially unfolding over decades. What happens when it vanishes? Will Jupiter's atmosphere reorganize? Will new storms emerge to fill the void? Or will the planet's entire weather system shift into a new configuration with consequences we can't predict? In July 2016, NASA's Juno spacecraft entered orbit around Jupiter. Unlike previous missions that flew past quickly, Juno was designed to orbit pole to pole, diving deep into Jupiter's radiation belts to study the planet's interior structure and atmospheric dynamics. What it found has rewritten much of what we thought we knew, including about the Great Red Spot. Juno's microwave radiometer can peer through Jupiter's cloud tops, seeing layers of atmosphere invisible to regular cameras. When it turned this instrument on the Great Red Spot, scientists expected to find a shallow feature, a storm rooted only in the upper atmosphere. Instead, they found something staggering. The Great Red Spot extends at least 300 kilometers down into Jupiter's atmosphere, possibly much deeper. To put that in perspective, if you stacked 3 Mount Everests on top of each other, you'd still be short of the Great Red Spot's depth. This isn't a surface feature, it's a titanic column of rotating gas, a storm with roots that may reach toward Jupiter's mysterious water layer, a region where temperatures and pressures are high enough for water to exist as a liquid, despite the lack of a surface. Juno also detected complex structures within the storm. It's not a simple vortex. The Great Red Spot has a cold core, surrounded by a warmer ring, with temperature variations that suggest complex vertical circulation. Hot gas rises, cool gas descends, creating a heat engine that somehow sustains the storm against the friction and turbulence that should dissipate it. Lightning. Juno detected lightning in the Great Red Spot, flashes of electrical discharge in a storm where water clouds are scarce. On Earth, lightning requires water droplets and ice crystals to separate charges. On Jupiter, with its hydrogen-helium atmosphere, the mechanisms must be different. Ammonia might act as a water substitute, forming mush balls, hailstones of ammonia and water that fall through the atmosphere, generating charge separation as they collide with droplets. These lightning flashes are enormous, hundreds of times more powerful than Earth's strongest bolts. The Great Red Spot isn't just windy, it's electrically alive, crackling with energy that could vaporize cities if it occurred on Earth. Most disturbing of all, Juno found that the Great Red Spot is influenced by Jupiter's internal heat. The planet radiates more energy than it receives from the Sun, leftover heat from its formation 4.5 billion years ago, plus ongoing compression as the planet slowly contracts. This internal energy drives Jupiter's weather, feeding storms from below in ways that don't happen on Earth. The Great Red Spot might be a pressure valve, a massive release mechanism for Jupiter's internal heat. If so, its survival isn't just about atmospheric dynamics, it's about planetary thermodynamics. The storm exists because Jupiter needs it to exist, to maintain some balance we don't fully understand. The Great Red Spot gets the headlines, but it's not alone. Jupiter's atmosphere is a battlefield of competing storms, some nearly as large, some potentially more violent. In 2000, 3 smaller storms, designated F, A, D, E, and BC, merged to form a new anticyclone called Oval BA. Amateur astronomers watching through their telescopes saw it turn red in 2005, earning it the nickname Red Spot Junior or Little Red Spot. For a moment, Jupiter had 2 great red spots. Oval BA has since faded to white, but it remains a massive storm, roughly the size of Earth. It orbits Jupiter independently, sometimes passing close to the Great Red Spot. When they approach each other, the interaction is violent. In 2002, before Oval BA turned red, it passed near the Great Red Spot and had a chunk torn away by the larger storm's powerful shear forces. There are other white ovals, massive anticyclones that haven't turned red. Some have survived for decades. Some form and dissipate within years. Jupiter's southern hemisphere, in particular, is crowded with these features, a churning mess of high-pressure systems competing for space and energy. Then there are the barges, dark, elongated storms in Jupiter's north equatorial belt. These are cyclones, low-pressure systems rotating in the opposite direction of anticyclones. They're less stable than the Great Red Spot, often breaking apart or merging with other features, but they can be just as large and just as violent. The Great Cold Spot. Discovered in 2017 using Earth-based telescopes, this feature is nearly as large as the Great Red Spot, but located in Jupiter's thermosphere, the upper atmosphere where temperatures should be high. Instead, this spot is 200 degrees Celsius colder than its surroundings. It's not a storm in the traditional sense. It might be caused by Jupiter's auroras or by interactions with the planet's magnetic field. But it's another reminder that Jupiter's atmospheric dynamics are far more complex than any single feature can represent. And these are just the stable features. Jupiter also experiences massive outbreaks, periodic disturbances where the entire banded structure of the atmosphere seems to convulse. In 2009, a large section of the south equatorial belt simply disappeared, fading from brown to white over several months. In 2010, it started returning, churning with new storms and turbulence. Jupiter is alive, not biologically, but dynamically, constantly changing, constantly surprising us. The Great Red Spot is merely the most persistent expression of this planetary restlessness. To truly appreciate the Great Red Spot's terror, let's compare it directly to Earth's most powerful storms. Hurricane Patricia, 2015. Maximum sustained winds of 215 mph, gusts to 253 mph. Diameter of about 300 miles, lasted about 24 hours at peak intensity. Pressure dropped to 872 millibars. Typhoon Tip, 1979, largest tropical cyclone ever recorded. Diameter of approximately 1,380 miles, half the size of the continental United States. Winds peaked at 190 mph. The Great Red Spot, winds of 400 plus mph, diameter of 10,000 plus miles currently, has lasted at least 400 years, possibly longer. Pressure structure fundamentally different, high pressure rather than low, but with pressure gradients that would tear Earth hurricanes apart. If the Great Red Spot was somehow placed on Earth, it would cover most of the North American continent. Its winds would scour the surface down to bedrock. Nothing we've built, no skyscraper, no bunker, no mountain fortress could withstand it. The storm would wrap around the planet, meeting itself on the other side, creating a global catastrophe beyond any disaster movie. But the comparison is actually unfair to the Great Red Spot. Earth hurricanes are fragile things, dependent on warm ocean water, specific atmospheric conditions, and the Coriolis effect. Cut off their heat supply by making landfall, for example, and they die within hours or days. Subject them to wind shear, and they tear themselves apart. The Great Red Spot has no such vulnerabilities. It doesn't need a warm ocean because Jupiter has no oceans. It doesn't make landfall because there's no land. The energy that sustains it comes from Jupiter's interior heat and the planet's rapid rotation, sources that aren't going away anytime soon. An Earth hurricane is a weather pattern. The Great Red Spot is a climate feature, a permanent part of Jupiter's atmospheric circulation. Comparing them is like comparing a campfire to a volcano. Both involve heat and combustion, but the scales are so different that the comparison becomes meaningless. Yet we keep making it, because the Great Red Spot challenges our understanding of what storms can be. It forces us to expand our definitions, to confront the limitations of Earth-based meteorology. If we ever hope to predict weather on exoplanets or understand the climates of gas giants in other solar systems, we must first understand this storm. Here's where the Great Red Spot becomes more than a curiosity. It becomes a template, a Rosetta Stone for understanding alien weather. Since 1995, astronomers have discovered thousands of exoplanets, worlds orbiting other stars. Many of these are hot Jupiters, gas giants orbiting incredibly close to their host stars. These planets are tidally locked, with one side permanently facing the star, the other permanently in darkness. Temperatures on their day sides can exceed 2,000 degrees Celsius. Do these planets have storms? Almost certainly, but what kind? The Great Red Spot provides our only reference point for massive, long-lived atmospheric vortices on gas giants. If we can understand why it has survived for centuries, we might predict what happens on these alien worlds. Some hot Jupiters show evidence of massive temperature differences between their day and night sides. Differences that should drive extreme winds, possibly exceeding the speeds of the Great Red Spot. Others have been observed with unusual brightness variations, possibly caused by massive storms rotating into and out of view. The James Webb Space Telescope, launched in 2021, is beginning to study these exoplanet atmospheres in detail. It's detecting chemical signatures, temperature profiles, and possibly even weather patterns. Every observation must be interpreted through models that are ultimately grounded in our understanding of Jupiter and the Great Red Spot. But there's a darker possibility. What if the Great Red Spot represents a stable configuration that most gas giants achieve? What if massive eternal storms are the norm rather than the exception? If so, then any future human exploration of gas giant systems, whether in our solar system or others, must account for these features. Trying to enter orbit around a planet where a storm 10,000 miles across is raging at Mach 1 speeds. Trying to navigate a probe through an atmosphere where wind shear can create forces that would tear spacecraft apart. The Great Red Spot isn't just a scientific curiosity. It's a warning about the environments that await us beyond Earth. We return to the question that opened this documentary. What happens when the Great Red Spot dies? The shrinkage continues. Every year, the storm loses a few hundred kilometers. Every year, it sheds more flakes, more streamers, more Earth-sized vortices into the surrounding atmosphere. The rate of shrinkage isn't constant. It accelerates and decelerates in patterns we don't understand, but the long-term trend is clear. Some models suggest the Great Red Spot could disappear within 20 years. Others give it 50 or 100. A few radical theories propose that the storm is actually entering a new phase, that the shrinkage is a prelude to a transformation rather than a death, that it might split into multiple smaller storms or reorganize into something we haven't seen before. But let's assume for the moment that it dies. That within our lifetimes, we witness the end of a storm that has existed since before the invention of the telescope. What replaces it? Nature abhors a vacuum, and Jupiter's atmosphere is no exception. The energy that currently feeds the Great Red Spot, heat from the interior, momentum from the planet's rotation, chemical energy from atmospheric reactions, won't simply vanish. It will go somewhere. Already we're seeing hints of reorganization. New anticyclones are forming in the southern hemisphere. The bands of Jupiter's atmosphere are shifting, with some expanding, some contracting, some changing color. The south equatorial belt, which faded in 2009-2010, has been particularly turbulent, suggesting that the atmospheric dynamics that created the Great Red Spot in the first place are still active. It's possible that a new Great Red Spot will form. Not immediately. There might be years or decades of relative calm, but eventually, the conditions that birthed the original storm still exist. The atmospheric instability, the shear between jet streams, the internal heat source, all persist. Jupiter will have more giant storms, or perhaps we're witnessing something rarer, the end of an era. The Great Red Spot may have been a feature of a particular climatic period in Jupiter's history, a period that's now ending as the planet's internal heat slowly dissipates over geological time. If so, future storms may be smaller, shorter-lived, less intense. Jupiter may be becoming calmer as it ages. We don't know. We've only been watching seriously for a century and a half. That's a heartbeat in Jupiter's 4.5 billion-year lifespan. The Great Red Spot may have formed and dissipated multiple times before humans ever pointed telescopes at the sky. It may be a recurring feature, a storm that dies and is reborn every few centuries. Or it may be truly unique, a once-in-a-planetary lifetime event that we're privileged to witness in its twilight. Why does a storm on Jupiter matter to us? Why should anyone care about a feature so distant, so alien, so fundamentally unlike anything we experience? First, pure science. The Great Red Spot is a laboratory. It's a place where physics operates at scales and intensities we can't replicate on Earth. By studying it, we test our theories of fluid dynamics, thermodynamics, and atmospheric science. We learn how energy moves through planetary systems, how storms self-organize, how complex systems maintain stability far from equilibrium. These lessons apply to Earth. Our own climate is a complex system, full of feedback loops and emergent behaviors. The Great Red Spot, despite its alien nature, teaches us about how large-scale atmospheric features interact with their environment, how they persist or fail, how they respond to changing conditions. In an era of climate change, these lessons are invaluable. Second, the search for life. Jupiter itself is almost certainly lifeless, too hostile, too energetic, too chemically extreme. But Jupiter's moons, Europa with its subsurface ocean, Ganymede, Callisto, these worlds might harbor life, or at least the conditions for it. Understanding Jupiter's atmosphere helps us understand the environment around these moons, the radiation they endure, the materials that might be exchanged between planet and satellite. And if we're going to search for life on exoplanets, we need to understand their atmospheres. The Great Red Spot is our best reference for massive gas giant storms. Every exoplanet we observe, every atmospheric spectrum we analyze, every temperature map we construct, they all rely on models grounded in Jupiter. Third, the human spirit. The Great Red Spot is beautiful. Terrifying, yes, but beautiful. It's a reminder that the universe is larger than our concerns, older than our civilizations, more complex than our theories. It has been spinning since before we knew what planets were. It will likely continue spinning, in some form, long after our species has evolved into something unrecognizable or faded into extinction. In a world of human-caused disasters, climate change, war, pandemics, the Great Red Spot is a disaster that has nothing to do with us. We didn't create it. We can't control it. We can only watch, study, and marvel. There's something liberating about that. Something that puts our own struggles into cosmic perspective. As of 2024, Juno continues to orbit Jupiter, its mission extended multiple times as it reveals new secrets. The spacecraft has made dozens of close approaches to the Great Red Spot, diving deep into the radiation environment to collect data that can only be gathered from nearby. Each flyby brings new surprises. The storm's depth, its temperature structure, its chemical composition, its interaction with Jupiter's magnetic field. Juno is mapping these features with unprecedented precision. The data will take years to fully analyze. Papers will be written, theories proposed, debated and revised. Our understanding of the Great Red Spot will evolve, becoming richer and more nuanced, even as the storm itself shrinks. Future missions are being planned. NASA's Europa Clipper, launching in the mid-2020s, will focus on Jupiter's moon but will also contribute to atmospheric studies. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, will arrive in the 2030s with instruments designed to study the planet as well as its satellites. These missions will watch the Great Red Spot's decline. They may witness its death, or they may discover that our predictions of its demise were premature, that the storm has depths and reserves we haven't detected, mechanisms of survival we haven't imagined. Either outcome is scientifically valuable. A dying storm teaches us about dissipation, about how energy disperses in planetary atmospheres, about the end stages of massive vortices. A surviving storm, against all predictions, teaches us about resilience, about hidden energy sources, about the limits of our models. The Great Red Spot, in its stubborn refusal to behave as expected, continues to be our teacher. Even as it possibly dies, it educates. Even as it confuses us, it clarifies the limits of our knowledge. It is, in the end, the perfect scientific object, always revealing, always concealing, always demanding that we look closer, think harder, question our assumptions. We began with a number, 8 minutes. That was the terror of Artemis II re-entry, the narrow window where physics decides if humans live or die. But the Great Red Spot operates on different timescales. Its window isn't minutes, or hours, or days. It's centuries, millennia possibly. While human civilizations have risen and fallen, while we've gone from Galileo's first telescope to Juno's microwave radiometer, the storm has watched. Not consciously, of course. It's just weather, just physics, just rotating gas. But in a poetic sense, the Great Red Spot is Jupiter's memory, a persistent feature in an atmosphere of constant change. It has seen comets strike the planet, Shoemaker-Levy 9 in 1994, leaving Earth-sized bruises in the cloud tops. It has seen the bands shift and fade and return. It has watched over a system of moons where volcanic eruptions and ice geysers, and possibly even oceans with life, continue their own complex dances. And it has watched us, first as a point of light in Galileo's telescope, a feature he noted but didn't understand, then as a target for increasingly sophisticated observations from Earth and from space. Voyager 1 and 2 flew past in 1979, giving us our first close-up views. Galileo orbited from 1995 to 2003. Cassini stopped by on its way to Saturn. New Horizons waved hello on its way to Pluto. And now Juno, the most intimate observer yet, circles in polar orbits that take it deep into the storm's domain. We are fleeting. The Great Red Spot, even dying, is eternal by our standards. If it vanishes in 20 years, it will have outlasted 20 generations of human observers. If it survives another century, it will see technologies and discoveries we can't imagine. If it regenerates, reforms, or gives birth to successor storms, it will continue to be there, a feature in the sky that connects us to the deep past and the distant future. The most terrifying storm in the solar system isn't terrifying because it threatens us. It doesn't. Jupiter is hundreds of millions of miles away, its storms contained by its gravity, its violence directed inward. The Great Red Spot is terrifying because of what it represents, the scale of nature, the persistence of physical processes beyond human timescales, the existence of phenomena so large and so complex that we can study them for centuries and still not fully understand them. It's terrifying because it's beautiful, because it shouldn't exist yet does, because it challenges us to expand our minds, to accept that the universe is stranger and more wonderful than our earthbound intuitions can grasp. As you watch this documentary, the Great Red Spot continues to spin. Winds of 400 miles per hour, temperatures colder than anything on Earth's surface, pressures that would crush submarines, chemistry that creates colors we can't fully explain, and a mystery that has endured since before Newton, since before the scientific revolution, since before the modern world. 8 minutes is the terror of re-entry. 4 centuries is the mystery of the Great Red Spot. Both remind us that space is not empty. It's full of storms, of heat, of forces that make our planet's worst weather look like a spring breeze. Jupiter is waiting. The Great Red Spot is spinning for now. And we are watching, learning, and wondering how many more secrets this giant world and its dying or transforming or eternal storm still holds. The most terrifying storm in the solar system isn't on Earth. It's out there, blood red and spinning, defying our understanding, demanding our attention, and reminding us that we are small, temporary observers in a universe of magnificent, terrifying, enduring power.